Okay, so I'm redoing this video so you can get a better idea of how they use Stonehenge. Now, what I'm saying is how they use Stonehenge. I'm not telling you the way it was built. I'm not telling you that the way people believe it is currently used is wrong. What I'm telling you and what I'm about to show you is how they actually used it as a calendar and how they were able to keep track of the solstice and the equinox. Okay, so there are 56 Aubrey holes. These are the Aubrey holes. All of these exterior holes here are Aubrey holes. There's 56 of them, so that would be 8 times. I'll get to that in a moment. Now, if we break it down into fours, okay, so let's begin with the Aubrey holes, okay? The Aubrey holes are these holes circling the exterior of the diagrams. What I did was divide them into their lowest terms, which is either 8 7 times or 7 8 times. So I elected to use 7 since 7's the lower number, and I began counting and then marking once I got to 7. Okay, so the Aubrey holes are complete. If you find a diagram like mine, you can just easily count starting at 1, and then we get to 7, 14, 21, 28, 35, 42, 49, and end up here finally at 56. This particular diagram doesn't have numbers, so same rules apply. Okay, so let's begin with these markers here. As you can see, I have this marked red, this blue, this blue. I have this marked red, this blue, and this blue. And you can see where the sun hits the altar on the morning of the solstice. Okay, so I finished my 7s 8 times, and as you can see, 1 through 7, 14, 21, 28, 35, 42, 49, 56. Did the same thing on this diagram, it just doesn't have the numbers. If we look here, we'll bring this over, okay? We have red here, blue here, blue here. That's the tilt. The blue represents the tilt. This gold one here represents the sun during the tilt, during the solstice. So we have the same thing over here. We've got the red representing the top of the earth when it's not tilted. We've got the blue representing the tilt. That's why if you look here and here, you see different circles because that's the indicator of the tilt. Now, using my protractor, I'm going to start bringing the latitude in, okay? I like to start here because this is the top of the earth, and then I like to do 7s going backwards. That way I ensure I don't make lines that don't correspond with this point. Same here. I'm going to start at these 7s and work my way back. I'll show you. So using my protractor, I'm going to create lines from this dot to this dot and scoot them back as they connect. Same thing on this diagram. Okay, so now we've got our first set of latitude down. All I did was create lines going there and backwards. Same thing over here. I use this blue line here because it's going to indicate a specific degree of latitude. So I'm going to begin my next series here and work my way back. Okay, so I have my second 7 of longitude here, and on here you can see that I've did the longitude. If you notice inside how it looks as though these lines are passing through there, that would be an indication of the sun's rays as they pass through. So you can see how symmetrical it actually is. And if you look here deep into the graph, you can see certain crossings at different points. Now I'm going to finish up the latitude in its entirety. Before I finish the latitude, I want you to notice that there is only 3 sevens left on each of these. That's because this is going to represent one thing, just like this is going to represent one thing, as opposed to 7, because this is going to represent 90 degrees at the top and 90 degrees at the bottom. Okay, so now we have our latitude finish on both, and I'm going to show you how it corresponds. So we've got 90 degrees here. We've got 60 degrees here, because there's not enough space going this direction to show you where the 60 is. So then we have 30 degrees, we have 30 degrees, we have 60 degrees, and then we have 90 degrees. So this 60 corresponds with that 60. This 30 corresponds with that 30. This 30 corresponds with that 30. We got 60, 60 here, 90, and this is 90. So now we have the latitude. Okay, so we got 90 degrees here. I know this is 30. No, this is 30. No, this is 60. And I know this is 90. Now there's a 60 here that separates these from this 90. So we'll put 60 here, 60 here. So now we have the latitude with the degrees. Okay, so now we're going to build on longitude. Here's how. So we know based off of this is the tilt, right? So we should start our longitude at the tilt. On this diagram, you'll see a 25, so I'll mark that as my prime meridian. On this one, you don't really see it, so I'm going to use an educated guess and mark this as the prime meridian. Okay, so now if we go back here to this one, this 25 is our prime meridian. Now this is 11, so if we look over here at 11, that's the ring of 30 pits called Y holes. So these holes out here represent the Y holes. Okay, so now, and if you see the darker marker, that's because that's longitude. If we look further inside where these black marks are, those are also longitude, but they're going this way. You see I have a marker here, and a marker here, and then I have a marker down here. So longitude, right? This equals 90 degrees. That's where this equals 90 degrees, this equals 90 degrees. That's where the prime meridian runs into the 90-degree mark, and this is where the 90-degree mark runs into it longitude-wise. So if you look at this, it's basically that point that I'm pointing out in this area. Okay, so if we start longitude-wise backwards from 90, this representing 90, we got 180, 150, 120, 90, 60, 30, and then we have the prime meridian. And we can count up 30, 60, 90, 120, 150, 180, and then we have 90 degrees, right? So if we look further in here, where if we look here, it says 29 or 30 pits. I believe it's only 29 pits because this area was left empty, probably because they already had enough indicators of where the sun was going to be, so they knew to leave this area blank. So I left that area blank and I did the longitude beside it. Now if you're wondering why this longitude is different from this one, is because this longitude, meaning the darker orange area, is based on this tilt right here. So it's going to have to return to its original axis once the equinox takes place. They compensated for that. So once the equinox takes place, those stones in between these exterior stones serve as longitude now. So if you look in between, we can do the same thing that we did here all the way to we start here with the 90 degrees representing that. Then we've got 180, we've got 150, 120, 90, 60, 30. The prime meridian, which doesn't exist in this one. Then we've got 30, 60, 90, 120, 150, 180, and then we have the 90 degrees. So that's once the Earth returns back to its tilt, they use this longitude. But for the solstice, they use this longitude. Okay? So let's check our work. Okay, so this is a diagram of the exterior of Stonehenge. So these 56 Aubrey holes. Okay, these aren't the 56 Aubrey holes per se, but they represent the rotation of the moon, right? So if we follow the moon's rotation, we know that we've got 2 holes clockwise every day. So we'll be doing 1, 2, and then mark 1, mark 1, mark 1, mark, and so on. Okay, if we look at the sun, we've got 1 hole clockwise after 7 days, and then another hole clockwise after 6 days. So we're going to move it 1 space at a time. And I started with June 21st because that's the day of the solstice. So if you move it 1 more time and add 7, you got June 28th. You move it 1 more time and add 6, you got July 4th. You add it 1 more time and add 7, 6, 7, and so on. So if we go back to this, right here at this blue marker, this represents the most southerly moonrise. You see on this one, I've got the same marker, and here we've got the most southerly sunrise. Okay, This is where the moon, most northerly moon set is, so that's when the sun comes back around at this point. All right, so if we start here at the moon rise, we will count this as June 21st. Okay, so beginning with what we know is the most southerly moon rise, right? We got it right here. So every other one, I made a mark all the way around. You see some called 90. You see some called 30. And you see some called 90 again, but it originated back to this spot. So we now have the lunar markers for how they determined nighttime. So if we begin here, the next one we know we add 7 days to, and then 6, 7, then 6, 7, and then 6, right? Bring you back to this. So this is how that one went, right? We got 7, 6. Well, we got 7, then 6, 7, then 6, and then 7. I put a split between here because during this time, this period of time and this period of time, the sun is in Cancer. So at night, you can detect where the Cancer constellation is going to be based on these dates. So it transitions from, let's see, mid-Cancer to Gemini. So if we looked at the totality of this and split it equally into 12s, we would have Cancer, then we have Gemini, Leo, we'd have, what's after that? Virgo, Libra, and so on. But what I'm going to do is show you the Fibonacci sequence that's embedded in this moon phase, and you can see how the sun can catch up. Now, okay, so I printed this out, and it says astronomical events in December. It said December 4th, total solar eclipse. Okay, so this is Seeker of the Cosmos. This is his sheet, it's not mine. So we're already familiar with the solstice, and we're not going to too much worry about this meteor shower. Let's concentrate on this total solar eclipse, right? So if I know this is June 21st, and I keep going around every 2 until I get through July, August, September, October, November, and December, the moon is going to be at one of these points. Now, if my calculations are correct, by the time the moon gets to one of these points, it'll be December 4th. And if we calculate the sun's movement using every 7, 6, 7, 6, 7, 6, 7, 6, the moon and the sun will share the same space. Now, depending on where well, this says a solar eclipse, so it's probably on this side because it would be the sun, the moon in front of the sun, so depending on where they meet is going to be the determination of what type of eclipse it's going to be. So this is how they were able to determine when eclipses were. I mean, 5,000 years ago, you didn't have anything but time. So they just probably generated a calendar for their own personal use based off of this. Now, when I initially started this research or this video, I told everybody that I did not know who built it. And I'm not disregarding anything pertaining to what people believe Stonehenge represents. But if you were to ask me why they went through all the trouble to make Stonehenge, I would have to tell you no differently than the movie Lucy. She made a reference about a car. If a car is traveling, let's say it's going into a loop, right? Let's draw me a makeshift loop. So if a car is traveling on this loop and it keeps coming back around and keeps coming back around, right? If you increase the speed so much, the velocity would make this car disappear. Like, so if it was going around so fast, it wouldn't be visible. So slowing it down is what makes you able to see the car going over and over again. I say that to say this. The people that I believe constructed Stonehenge just wanted people of this generation or generations to come to know that they existed, that life existed here. And this is proof. Like, not only were we here, we can show you that we were here. And while we were here, we did some pretty cool stuff. So yeah, so since we're able to track the moon by day, this is the one that I was using to track. I think I went all the way to August. I see. It looks like I did all the way to August. So, and I didn't incorporate the sun's movement. But like I said, the brilliance of this in its entirety is not only did it work during the day, it worked at night because they were using the constellations as markers too. So when you hear the expression as above, so below, this is exactly what as above, so below represents. And that's it for me. Thanks for watching.